Hello and welcome. In this video, I'll be covering the first half of the notes for the section 7.1, which is over identities, mainly some of the quotient identities, the reciprocal identities, Pythagorean identities, some even and odd function identities, and then we'll also get into, in the second video, or part 2 at least, this sum and difference identity. So this one will mainly just focus on how do I simplify and potentially manipulate different expressions that involve some of these identities, and utilizes a bunch of substitution property. So we'll go ahead and start talking about the basic trigonometric identities you can see on the screen here. All of the identities I'm about to talk about are things that you can find inside of the notes for this class, so don't necessarily have to pause and write all these down, but at least being familiar with them, or at least aware of what they are, is going to be helpful. So having relatively easy access to these while working through some of the problems that will be in your homework or in the examples here in the video will be beneficial, at least as far as like making the process go a little bit faster instead of relying 100% on memory. As you do more and more of these, the theory should really be that the more you do something, the easier it is to recall. So you may find yourself not needing to reference as much as you do more and more examples and you start seeing some patterns, but initially having either the formula sheet that I've printed off for the last couple of tests, or even just having the notes maybe printed off, having all of the identities that are identified here somewhere close by, I guess, should make the assignment go a little bit faster. But again, the main ones we have here are the reciprocal identities, which we should be relatively comfortable with, sine and cosecant being reciprocals of each other, secant and cosine, as well as tangent and cotangent. And then I have all of the different versions. So notice the formatting of these ultimately is just the reciprocal turns into 1 over whatever the other function is. So like cosecant, for example, the first one here, cosecant of theta is just 1 over sine of theta, and so on and so forth. So being able to utilize that in some way, shape, or form, you thinking of like a substitution. Basically, if I had cosecant of theta somewhere in an expression, I would be able to replace it with its equivalent value, this 1 over the sine of theta. But anyway, if we go ahead and maybe look at the next ones, the quotient identities, these really just come from, if you think of the unit circle, I've got y over x for this. Y over x really was how we computed the tangent values, but if you also recall, the y values on the unit circle were the sine of each angle, and the x values were all the cosine of the angle. Hence, the formula for tangent, if it's y over x, it's technically the same as doing a sine of theta over the cosine of theta. And since tangent's reciprocal is cotangent, we can relatively quick and hopefully easy see that cotangent of theta then just would be the flip version of that, so it would just be x over y, or a cosine over a sine. Now, the even and odd identities honestly are not a very common occurrence when it comes to at least their use with some of the things that we're going to be doing with these identities, but they still exist, so we'll still discuss them at least. On occasion, if you notice that we have negatives inside of certain trig functions, so notice all of these on the left have a negative theta inside, and notice the top 4, all of these are considered the odd functions, so they actually have origin symmetry, if we think back to a prior chapter when we discussed even and odd. But origin symmetry for each of these graphs basically just means if I plug in a negative version of an angle, it would be the same as plugging in the positive version but then changing the sign of it. So that's where the negative out in front of each of these is coming from. Then we have 2 even functions, which are symmetric about the y-axis. The only 2 that have the y-axis that perfectly cuts it in half are the cosine as well as its reciprocal, the secant graphs. So these ones are basically, if I plug in a negative angle, it would be the exact same as if I just plugged in the positive version of the angle. So oftentimes it's the even ones that we'll take the most advantage of, but technically, again, these identities do exist. The next few that we'll have are called the Pythagorean identities. And really, it's just this group of 3 on the left, and then the alternate forms are just isolating different parts of each of those equations. So notice the Pythagorean identity, the very first one there, sine squared of theta plus cosine squared of theta equaling 1. Each of the alternative forms are basically just taking a term and then moving it over to the other side. So like with this example, for sine squared of theta, I could just subtract the cosine squared of theta over to the other side, and that creates this new version of that same identity. So it's really just being able to manipulate moving things from one side to the other that is kind of happening here with the alternate forms that are on the right. Now, as far as where do these come from, if we really think about how sine squared plus cosine squared equaling 1 should come to be, if we think about the equation for the unit circle, which is the, not y squared, or not x squared, but y squared. So x squared plus y squared equals 1 is the equation of the unit circle. Remember, it's a radius of 1 centered at the origin, so this would be my formatting. And just like I mentioned before, the x's and y's really can turn into sines and cosines. So the y is sine, x is cosine, so y squared really matches the sine squared part, x squared matches the cosine squared part, and then equals 1 obviously is just staying the same on the right side. The reason these are the Pythagorean identities is it's really just utilizing those special right triangles as well as the Pythagorean theorem, a squared plus b squared equals c squared, and then just creating just a different version that's more in a trigonometric form. Now, as far as what can I do with that to create the other ones, this is where it's kind of a combination of the identities mentioned before. If we think in terms of how could I create maybe a tangent, tangent is the same as sine divided by cosine. So one thing that we could do potentially is take this top one and just divide everything by cosine, and just making sure that the power matches. So if it's sine squared, I just divide by cosine squared. Ultimately, if I then replace each of these with whatever their either reciprocal identities or quotient identities are, notice sine squared of theta over cosine squared of theta would create this tangent squared of theta. Cosine squared over cosine squared, that would create the 1. And then the last part would be 1 over cosine squared. Its reciprocal is secant, so 1 over cosine squared must be secant squared, which creates that third term. And then, like I mentioned before, all of the alternate versions over here would just be picking something to isolate. So if I wanted to isolate the 1, I would move the tangent over, and that creates the, not that one, the first one here, where I would subtract tangent squared from secant squared on the other side. Or the other option would have been to subtract the 1 over to get tangent squared by itself, which then would create this last one. Similarly, if I wanted to try and create this bottom one, instead of dividing everything by cosine like I did here with my first example, let's say I maybe go ahead and get rid of all of that. If I actually divided everything by sine squared instead of doing cosine squared, now it creates a cosine over a sine, which is cotangent. Again, all of them just getting the same power. That way I still have the Pythagorean identities that are being used here, so powers of 2 are required with each of these. Sine squared over sine squared creates the 1 like you can see here. Cosine over sine is cotangent, so if they both have powers of 2, it would become cotangent squared. And then the last one, 1 over sine, that's cosecant, or its reciprocal, so 1 over sine squared would be cosecant squared. And again, as mentioned with the other examples, the alternate forms are just isolating different parts of that. So as far as the bare basics of where they come from, hopefully this is helping at least solidify that part. We're about to jump into some examples where we can actually see like why we would actually need to know these. But the general concept we're about to kind of embark on is going to be a lot of substitution property. Ultimately, we're going to try and simplify things that involve parts of these, or maybe parts of expressions contain or match certain ones of these identities. And ultimately, we'll just try and replace and hope that things either start canceling or combining in a nice way. So hopefully I can make something that maybe looks pretty complex turn into a relatively more simple, hence the name simplifying, but try and make it a little bit easier to deal with expression when it's all said and done. So that's, again, what the next 3 or 4 examples are going to be about. All right, so the first example here, relatively straightforward, just tells us to factor and simplify. So when it comes to this specific one, things to keep an eye out for, this is the expression we have, is to maybe look at how many terms we have. If it ever says something about factoring, look to see if it's maybe in a quadratic form, or maybe it's in a form where it's just let's take out something that they have in common. In this case, I've only got 2 terms. They don't really fit any sort of quadratic model, so this is more of a let's just take out what they have in common. So hopefully with relative speed or maybe even just ease, we can recognize that both terms do have at least a cosine. In fact, they actually have two cosines in common. So I should be able to factor cosine squared of x out, which then is going to leave on the first term the sine squared of x. And then from the second term, cosine squared out of a cosine to the fourth should actually leave the other cosine squareds of x's, or if you think of it as four cosines being multiplied together, I took two of them out front right here, so that means the other two need to be left there. So anyway, hopefully that's making sense as far as like how I can just take out something in common. It's really no different than if I had something like, what if I had 2x plus 5x squared, and I said factor? Well, it would just be take x out. That leaves a 2 from the first term, and it leaves the 5, but also one of the x's from the second term. It's really the same general concept. It just is slightly different functions, obviously, but also slightly different powers than that random example I just created. But anyway, at this point, hopefully we can recognize that what that just turned into inside the parenthesis actually matches one of those Pythagorean identities. Sine squared plus cosine squared had a value that's equivalent to 1, so what we could do is just replace that whole thing with 1, and then the other part that I factored out technically just stays out front. And if we look at what that would turn into, that would just stay cosine squared of x, because multiplying by 1 would not really change anything. So I was actually able to take something that was two terms, turn it into one term, but also actually only have to worry about one trig function, whereas originally I had two. So definitely when it comes to the idea of this quote-unquote did I simplify, I definitely did make this fewer things, so that in theory is more simple than where I started, but also it's fewer types of functions. So it's kind of a double proof, if you will, as a way to kind of prove that yes, we truly did simplify or make it more simple for ourselves, that if I needed to use cosine squared of x compared to the original, cosine squared of x in theory should be a little bit easier to manipulate in like a follow-up step if I needed to do one. Alright, the next couple of examples here, just more of the same. This was going to be something where maybe I might need to do a little bit more than what we had done in that last one, since it was pretty quick and easy, but this one we just kind of look for things that we can maybe manipulate. So my eyes initially get drawn to the negatives inside of each of the parentheses, so cotangent of negative theta. I kind of feel like that negative theta is something we should deal with, so this is where the application of those even and odd functions will become useful. So if I wanted to switch that negative theta to a positive theta, ultimately according to the odd identity for cotangent, I could just move a negative or put a negative out in front, and now my angle inside would be its opposite, or in this case a positive. Similarly with cosecant, since that's also an odd function, I could say that the negative that would be inside I could actually say is the same as a negative outside if I change the angle to a positive or its opposite. And at this point now we have those negatives out in the open where they can now interact. So those two negatives that are outside, if we think about it, a negative divided by a negative should actually turn into a positive, so why not just go ahead and drop them? And also, I don't necessarily have to have the parentheses, so I'm going to kind of try and simplify some of the writing and just write it as theta instead of parenthesis theta. Now it would turn into something where, let's think of maybe some options. So one thing we could do is split it into two separate things being multiplied, because you can kind of picture like it's a cotangent over 1, and then a 1 over a cosecant, really, if we wanted to break it down. That way we can kind of see it as two separate parts instead of one big giant thing. And now it would be, let's think through our options of things that could be replaced or could be plugged in place of each of these things. So cotangent, if we were to look at some of those identities, has a couple of options. One of the options would be to switch it to its reciprocal 1 over tangent, but that doesn't seem like it would interact very well with this cosecant that I have kind of hanging off to the side here. So switching that to 1 over tangent, even though yes, it could happen and it would be a correct step, it just doesn't necessarily get us going in a direction that seems like there will be something to pursue afterwards. So the other option we had for cotangent would be to switch to cosine over sine, and you'll hopefully see in the next step that why that makes sense is if we look at our other part, 1 over cosecant of theta really only had one option, and its option was to switch to a sine of theta, where it's no longer as a fraction. Now you might be able to see right now, but if you haven't, hopefully you could notice that this sine of theta really could be like it's over a 1, And so we could just say, well, now the sine of theta divided by sine of theta that I've created will cancel out, and so all of this actually was able to simplify to just a nice and simple cosine of theta. So what was relatively ugly at the beginning with a couple of negative angles actually turned into a relatively simple or easy to deal with trig function where there weren't even any powers or negatives at all. It was just the cosine of theta is what it was able to simplify to. So this is kind of one of the peculiar things with these trigonometric functions, is there often is a way that you can always manipulate it to make it turn into something else. It's just a matter of what is that something else going to be. Is it going to be better or is it going to be worse than wherever I started? Our general approach with most of these is going to be take something that maybe starts out kind of ugly and turn it into something that actually is a little bit less ugly, if you want to think of it that way, or at least just maybe a little easier to deal with. Now the second example, if we go ahead and jump over to it, this one, if you look at each of the parts, one thing that kind of catches my eye right off the bat is there is this 1 minus cosine squared on the bottom that matches one of the Pythagorean identities, so I could just automatically go straight to what that's equivalent to off to the side here. And 1 minus cosine squared of t is actually equivalent to sine squared of t. And why that actually is kind of nice to do in the denominator here is, now notice I started with 3 terms and I was able to turn it into 2 terms. But the other kind of nice part is the 2 terms actually have something in common. So if I think ahead, that might be able to turn into something where I could factor a sine out. In this case, they both have sine of t, so I could factor a sine out, kind of like the first example, and just write what's left. So sine squared, if I took one of the sines out, leaves the other sign. And then if I took sine out of itself, it should leave a 1, and then the subtraction stays in between. Now the top, if we start looking at what the top might have as options, this has 3 terms. Everything is already in terms of sines, except for that last term being a constant. So I'm hoping that if we look at that, that really does seem like it's a quadratic form. After all, it does have a power of 2 on the first term, a power of 1 in the middle, and then a constant at the end. So if it helps you, we could kind of maybe off to the side just think of that as, well, what if it was just x's instead of sines? Well, it could be 2x squared, then plus a single x, and then minus a 3 at the end. And from here, I could now maybe try and do like a reverse Punnett square, and just think of what would go in each of the spots. So 2x squared in the top left, negative 3 in the bottom right. And from here, I would want to figure out what the a times c value is, which is negative 6. So what multiplies to that negative 6 that will add to the 1 in the middle? Well, that would be a positive 3x with a negative 2x. And then on the outside, it's just kind of figure out what would go into each of these. So if I just go maybe this first column, or sorry, not column, but first row there, the only thing that they have in common is x. So if I now take an x out of that, now I should be able to kind of just work my way around. X times what would make 2x squared for the 2x on top, and then 2x times what would make the negative 2x on the bottom left? Well, that would have to be a negative 1. Then negative 1 times what would make the negative 3 here? Well, that would have to be a positive 3. And we can now see that the factors would be a 2x plus 3 and an x minus 1. However, with this being more of a quadratic form involving trig, I could go ahead and just set up those 2 parentheses, but instead of having x's in these 2 spots, I'm actually just going to put sine of, I guess in this case it's t, so it'd be 2 sine of t plus 3 is one of them, and then 1 sine of t minus 1 is the other one. So again, in the next step, we would just keep that factored form. Notice on the bottom I did not distribute out. That actually is intentional. Usually it's best to kind of leave denominators alone until you absolutely have to multiply it out, because after all, what we're trying to accomplish is for things to maybe become more simple. In other words, try and cancel. So if I keep the bottom in a factored form, potentially if I'm able to combine like terms on top and then maybe factor, I might be able to notice that there are some common factors that can cancel out. I'm thinking at this point you probably have noticed that there is a sine of t minus 1 on top and bottom, so they actually would be able to cancel each other out or turn into a pair of 1s. And so ultimately now at this point I've got 2 sine of t plus 3 all over a sine of t, which ultimately what I could do from there is just split that into 2 fractions where they're both over sine of t. So 2 sine of t over sine of t plus 3 over sine of t, basically just kind of the reverse of what we would normally do when we get a common denominator. Instead of combining and making it one single fraction, actually taking one fraction and splitting it up. Why that's nice is the first one, notice the sine of t's now actually cancel, leaving me just 2. And then the second one, 3 over a sine of t, if we wanted to get the sine out of the bottom, we could just utilize its reciprocal identity, keep the 3 on top, but then flip technically the sine of t, which would turn into cosecant of t, and voila, we've been able to turn into something that looks a little bit more beneficial, or a little bit easier to deal with maybe, compared to the beginning. After all, the beginning had a whole bunch of sines and cosines, was a big fraction. I had 3 terms on top, 3 terms on bottom. Like, that was pretty intense to start, but it was able to kind of dwindle down, or at least utilizing these identities, kind of turn into this relatively simple expression here where it just doesn't have any fractions anymore. Now, if you are more of a fan of sine of t, you could technically have left it as 3 over the sine of t if you prefer that function over cosecant. But again, that's kind of the trickiest part of the simplify, is how do I know when to stop? Well, ultimately, if you get to a point where the next step would make the answer that you have seem like it actually is a little bit more worse than where you just were, that often is usually meaning that's a good stopping point before you do that next step. So here I think what I just boxed there would be the, I guess, easiest visually to deal with, but maybe the step before where it would leave it as 3 over sine of t could also be almost as easy to deal with, or maybe even the combined versions. Just kind of depends on context. Really, right now, we're just trying to figure out what can these things turn into. So you just kind of start with, pick something that you can hopefully replace, and just see if that takes you down an avenue where things start to combine, or like these examples, maybe things start to cancel if I have fractions involved. But that's kind of the general idea. We're just trying to make things, again, look more simple. Go ahead and move on to another example here. Hopefully it's starting to kind of make sense. I don't expect it to be fully 100% like, oh yeah, this is exactly what we do, but at the same point, hopefully this is turning into at least some sort of pattern recognition that we're seeing here. Now, for this specific example, it does say that we should add and simplify, so one thing we could do right off the bat is recognize that we have a fraction added with something that's not a fraction. So I could think, you know what, let's put that over 1 and get a common denominator. The other option is we could immediately go, well, tangent seems like it doesn't really interact with sines and cosines like the first part has, so maybe let's just switch it to sines and cosines since it has that as an option. So in fact, that would actually be the beginning I would go with personally, but not every single problem has to be worked through in the exact same way. In other words, if we wanted to, we could get the common denominator by multiplying top and bottom of the tangent of x by the 1 plus sine of x, but I kind of just want to get the tangent out of the way as soon as possible, so I'd actually just go ahead and just rewrite it as its equivalent value, or identity, which technically was a quotient identity, as sine over cosine. So now is when I would look at it and go, well, technically now I'm kind of stuck. I've got fractions that are being added together, so I do need to get a common denominator. So in this scenario, it's really just the two denominators I see multiplied together will be the common denominator. So it kind of tells me this first one has to get multiplied by cosine of x on top and bottom, so it now has a cosine on the bottom. And then the second one would have to get multiplied by the other denominator, 1 plus sine of x. And again, multiply that through on top and bottom. That way it's really like I'm just multiplying by 1. But now I could like combine this together and say, well, the denominator now has cosine of x times a 1 plus sine of x. And like I mentioned before, usually it's best strategy to try and keep that in factored form as long as possible. If I need to multiply it through and turn that into cosine plus sine times cosine, we could do that eventually, but again, hold off on that urge. But the numerator, this is where I actually will want to multiply things out. That way, hopefully I can get some combining like terms to happen, or maybe some identities that I can replace to start showing themselves. But anyway, if we go ahead and figure out what those things on top would be, cosine of x times cosine of x for the first fraction would give me cosine squared of x. And if I distribute the sine of x through the 1 and the sine, that would turn into sine of x times 1 is sine of x, plus sine times sine should give me a sine squared of x. And now I'm hoping that we see like the cosine squared plus the sine squared, those two things right there. If I were to add them together, so in other words, if I combine them, that is one of those Pythagorean identities, that actually will turn into a 1. And then I still have the sine of x, or the plus sine of x technically, that would be left in the numerator. But again, to try and connect the dots, the cosine of x plus sine, or sorry, cosine squared of x plus sine squared of x had a value of 1, so I was able to replace that with its value. The sine of x that was there just stayed, and then on the bottom I still have the cosine of x that is still multiplying with the 1 plus sine of x. As you might have already seen or recognized, the 1 plus sine of x that's on top, if I group it up, technically would be able to now reduce with the 1 plus sine of x that's on the bottom. Since I don't have something left on top, I would maybe want to say, well, technically there's a 1 as a placeholder, so this would actually equal 1 over cosine of x at this point. So something that was pretty ugly to start and kind of ugly here in the middle, stuff canceled out pretty quick, now turned into something pretty simple. And now the last step would be, let's just maybe rewrite that so it doesn't look like a fraction. And in fact, 1 over cosine of x equals its reciprocal secant of x. And so we can go ahead and simplify that whole thing down. So notice where we started here and what it's equivalent to here at the end. I hope we would all agree that the secant of x would definitely be easier to do secondary steps with compared to whatever the original was. Especially if I just said, hey, let's let x equal pi 6, what would the value of it be? Well, plugging in pi 6 in 3 spots compared to only 1 spot, it's definitely easier to do just the 1 spot where it would just be what's secant of that value and then writing it down. All right, now moving on to our last example, at least for this video. There is going to be a part 2 that covers the second half of the notes over the sum and difference formulas, but for this one, if we go ahead and look at what's here, it gives us some expression, or it wants us to express the square root of 9 plus x squared in terms of only trigonometric functions. So in this case, notice it's actually telling us specifically what they want x to equal. There is some rhyme and reason behind that that's a little bit more related to a different class. But as far as this example, it just wants you to kind of practice the idea of, if you have this and I want you to substitute this in, how can we simplify that utilizing some of the identities we've presented? So with this one, it would be, if I wanted to go ahead and simplify or do that substitution, the right side of it would be able to say is now equivalent to 9 plus what I'm substituting in. So I'm replacing x with 3 tangent of theta based on the instructions of the problem. It would be raised to a power of 2, which I could then simplify and say that squaring that, 3 squared would give me a 9 as the coefficient, and then tangent being squared would become tangent squared of theta. And now it would be, how could I maybe manipulate whatever's inside? So one thing I noticed right off the bat is they both have a 9, so we could try and factor like 2 of the previous examples. So if they both have 9, I could factor a 9 out. Creates this new expression, and now we might recognize, if we have a reference page close by, that that technically will turn into a secant squared of theta. It would still be inside of the radical, but I still would have the 9 hanging out inside, but I was able to make 2 things turn into 1 thing. So again, that's the general process that we would be doing when it comes to trying to make something quote-unquote simplified. At this point, because it's now a product, I should be able to actually split up that radical over the 2 parts that are inside. Square root of 9 producing a 3, and square root of secant squared of theta actually just turning into secant of theta. So the square and square root technically cancel. And again, it's on the left side, it was saying let's go ahead and express this specific thing in terms of trig, where if I do that substitution, notice it actually turns into something that doesn't have a radical on it. Now, one thing that we can maybe recognize at this point is we could isolate the secant of theta by just dividing both sides by 3. So off to the side here, I'm going to go ahead and rewrite this in this space in the top right, but that would now give us secant of theta is equivalent to the square root of 9 plus x squared all over a 3. And notice the last part of this question actually specifically is just wanting us to now find the values of sine and cosine. Well, if this is secant, remember cosine is just the reciprocal of that, so let's try and separate this a little bit. So cosine must just be the flipped version of what we just created. Now, oftentimes when we have the radicals like this end up in the denominator, we would then rationalize. But because there's variables involved, we actually just leave it as is, because after all, if I plugged in maybe a nice number that would go in place of that x that actually would get rid of the radical or would stay a perfect square on the inside, it would make it to where I didn't necessarily have to rationalize. So this is, again, we only usually rationalize if it's just a value on the bottom. Since this is more of an expression, we would just leave it as is. Now, another thing we could do at this juncture is we could utilize what we know from SOHCAHTOA and just draw a right triangle. If I know that cosine is this ratio, that would mean if I call that my theta, that the adjacent side would be the 3, the hypotenuse would be the square root of 9 plus x squared. And at this point, to get the last side, it would be square those two things and subtract. So that ultimately would be 9 plus x squared, then minus 3 squared, which is 9, and then inside of a big square root, which notice the 9's would cancel, and I'd be left with the square root of x squared, which is just x. So if I now wanted to figure out what is the sine of theta utilizing that triangle, the sine is going to be the opposite side, which was x, over the hypotenuse, which still was the square root of 9 plus x squared. And this idea in this class, for the most part, is not going to make sense why we would care to be able to do those skills. However, in a future class, AP Calculus, or even just a regular calculus class, this ability to manipulate and maybe utilize trig in a way that makes something that maybe is complex, such as a radical, turn into something that's more trig related. There is a rhyme and reason, and actually does simplify parts of that. It's just, again, we probably won't necessarily see that connection until we get into that class. So this is more just building the skill of how can I manipulate, how can I maybe replace things that have x's and turn them into some trig functions as like maybe the main thing that you can kind of take away from this. But ultimately, that's all this question was wanting us to do, is just kind of practice that skill of how could I make something that has a radical no longer have a radical, at least not with the variable I might want to deal with. So trying to get something in terms of theta, in other words. And notice I have secant of theta, cosine of theta, sine of theta. Technically, I could do all 6 trig functions if I really wanted to. I could bring tangent into it, cotangent. I guess there's only one more, cosecant. I could figure out all of those where it would just be reciprocals of a lot of the other ones. But again, now that I have my triangle here down on the bottom right, I should be able to do any of those 6 if I really needed to, if I had maybe like a follow-up step afterwards. Anywho, the whole point of this first half of the video is just more, again, getting you, one, familiar with some of the identities that we can use to replace certain parts, but also two, kind of to see some of the examples of, if I do this, here's what might happen, which is a very useful skill as far as simplifying, knowing that there's a cause and effect. If I substitute something in, where will that take me? Is it going to make things better or worse? That's really kind of the main thing that this group of examples is hopefully trying to solidify for you. But as mentioned before, there is going to be a part 2 of this. I just didn't want to make this turn into a super long video, even though this one probably is decently long. But kind of trying to chunk it down to make it a little bit easier for watching purposes. But to be continued with this one, the part 2 is going to be over the sum and difference formulas, as mentioned earlier. So if you need some practice with that, or you need some extra explanation for it, go ahead and maybe tune into that one here in a moment. But as always, if you have questions on any of the types of problems that I've presented so far here, please just come find me, give me a chance to help, and hopefully we can get it figured out. But anyway, appreciate you taking the time watching this video if you have, and we'll go ahead and catch you next time.